yesterday I got stuck in my first talk actually. So we came to the minimal models, which are models where the sum over Verma modules is finite. We introduced characters and some representation theory, and something which was crucial were these so-called null fields, which are descendant fields which are also primary, and those you want to factor out. And once you have done that, you arrive at this amazing and very strong result. So if you express the central charge in this parameterization with M, then it turns out for a model to be unitary, that is to say to be probabilistic, M has to be an integer larger than or equal to 2, and moreover all the critical exponents are given by this parameterization involving the same M and integers R and S, which range over some interval, and these. Oh, thanks.
But there is even better. There is this game.
Oh yeah, sure. Well, I like the laser pointer. So these integers here will index all possible critical exponents in your given model. And all of that has been attained without ever writing down what the theory really was, without writing down what its energy or action was, just by exploiting conformal symmetry. So,
excuse me, Jesper?
Yes.
Are there interesting models where the central charge is bigger than 1?
Yes.
Yeah. And
there are, but they have then either to be non-unitary, or they have to have a bigger symmetry than just the conformal symmetry. So, for example, it can be some of those super-conformal or extended conformal field theories.
And is it possible to have such a model, say, two different models with the same conformal charge and with different content of the, what are they called, primary operators?
Well, according to this result, and I mean with these hypotheses, it's not.
I see. So that part of it is valid for any central charge. The unitary condition is just when C is less than 1?
Right. So the unitary condition gives you that M should be an integer larger than or equal to 2. So this is a very strong result. Okay.
Isn't it possible that you have different multiplicities for you can have fields?
Right, multiplicities mean that you want to find out how the holomorphic and anti-holomorphic sectors couple, so that means that you are on a torus, so I'll speak a little bit about that later on. Okay, what I want to show now is that correlation functions can be found by solving differential equations. So how does that go? Write here a generic descendant state, which I'll call chi because I will assume that it's a null state. So it's a linear combination with some coefficients, and then the sum over all descendant operators of some primary field phi at a given level. So all of the rest is just notation. So there's a string of these L operators acting here with integers R, I. So those I collect as a y, that's all the indices, and size of y is the total level. So this is a generic descendant state, and let me suppose that it's a null state. Well, now we saw yesterday that descendant states, when they act on, when they are multiplied by an arbitrary product of primary fields, so this big X here is always just a product of primary fields. And we saw yesterday that such a correlation function here for any descendant is expressible as the correlation function of the corresponding primary field acted on by some differential operators, which I defined yesterday. And now, since we are factoring out this null state, well, then the chi is simply 0, so this is 0. So here you have a differential equation.
How did we know chi was a null state?
Because I'm supposing that.
Well, but it's not stated on the side.
I'm sorry, but I said it.
Okay, all right, okay, so if chi is a null state.
Yes. Was supposed to be implied by the notation. Okay,
Well,
so
but they used the letter chi, okay, all right.
so now we saw also yesterday that 2 and 3 point functions are completely fixed by conformal invariance. 4 point functions have one free parameter. It's because you can map any 3 points to 0, 1, and infinity, which are trivial points. So the fourth point is going to define some coordinate. So if you take 4 point functions, you are just going to get a linear ordinary differential equation of eta, which is called the anharmonic ratio, where you can think of it as being this leftover z. Maybe some of you know a very famous and important paper by Cardi, in which he establishes that the probability of having a percolation cluster cross a large rectangle is equal to some hypergeometric function. So what does he do to derive that result? It's really pretty easy once you know all of this. So on the rectangle you have 4 corners. In those 4 corners you insert a given operator, which is chosen in a smart way, so that it says something about what the boundary conditions are going to be, something about that from the interval which is one side to the interval which is the other side. You can have a crossing or you cannot have a crossing and something. So you do a little bit of adding and subtracting, and then those operators turn out to have a null field on level 2. So you get a second order differential equation, and the solution is a hypergeometric function. So that is how a result like that is obtained.
Well, you also have to know that conformal theory is that percolation is conformal,
Sure, yes.
which is difficult problems to unsolve.
Well, now for percolation it's proven that
For
things
only
are
for example,
conformally
but it's
invariant.
not for square lattice.
I wanted to get back to what I called minimal models. So a minimal model is not necessarily unitary. I was talking about unitary models. Minimal model is one where the number of these Verma modules is finite. So you can actually arrive at a result which looks a lot like the one that we had before, except that you have 2 integers, m and m prime. And the former result, m prime, was just equal to m plus 1. So if you require that this operator product expansion closes over a finite number of primary fields, then after quite a long reasoning, you get that the central charge and the exponents satisfy this, where now m prime is free not to be m plus 1. And with even more work, you can establish the so-called fusion algebra. So what this means is that I'm writing here very symbolically the operator product expansion of any 2 primary fields indexed by these integers r and s. So yesterday I had the complete say version of this formula. So what it means is that when the coordinates of these 2 guys approach, then I'm going to get a sum of other primary fields along with all their descendants. So here, just to keep notation simple, I have suppressed all coordinate dependents, I have suppressed all descendants. I'm just writing which primaries are coming out. And so there's some formula saying exactly which primaries will come out when you take 2 other primaries and you approach them. So I will go a little bit fast here. So we also needed to construct these irreducible representations. So we had these.
Modules are over the previous algebra.
Sorry?
We defined an algebra, and these modules are over modules on this algebra?
So I had the V's, right, which were these Verma modules. So a primary field with,
so
with all
from-
its descendants.
From the previous and
And the M. And the M was the thing that remains once I have factored out all the null states, quotiented out all the null states. So it turns out that when now R and S are just these integer coefficients of, I'll finish my sentence, when they are the integer coefficients determining a primary field, it turns out that generically this Verma module contains two other Verma modules at integer levels. And those two can be then identified with null fields, so they have to be taken out. Okay, so that looks easy. So I take this module and I take out that module and that module. The problem is that the two of them intersect. So I had to put something back. So I believe you call that inclusion exclusion. So there's going to be an infinite number of inclusions, exclusions, so additions, subtractions, and in the end what you get out, and let me just go to the end, then I'll take your question, is that this character here can be written in the following form. So the character was counting for a given primary all the descendants which happen at a given level, right? Remember that it was this generating function, and it's a difference of something where something is this complicated thing. So this is known as the Rocca-Caridi character formula. So this is telling you for a given primary field exactly how many descendants you have at any given level. So those.
It was about the fusion formula you wrote. It looks a lot like the Krebs-Gordon decomposition. Do you have SL2 represented? It seems like you have two SL2.
Right, there is a SL2 in this whole story, yes. Okay, so now I have gone over the hard part. So let's take a small summary. What have we achieved up till this point? We have classified a countably infinite series of minimal models. We have never written down any lattice model or continuum action. We have gotten all the critical exponents from this catch table, so the H's, and we have gotten all the corrections to scaling from the characters. Well, that's pretty nice. The only thing which remains to be done is to somehow identify the models that we have classified with some microscopic models.
Could you just remind us in this language what is a critical exponent?
It's the H, the conformal weight. Because the H tells you how the algebraic decay of two-point functions, for example. How can I ever identify this, for example, with the Ising model or something nice? Well, there are various routes that I can try. Either I can try to get some of the critical exponents by other means, for example, by solving the model exactly. If I knew them, then I would be able just to look up my catch table and see which one I had got. Another thing that I discussed briefly yesterday is that it's possible to extract the central charge from numerical simulations. And once you have the central charge, all the rest will follow. Or a last option is that now that you have this fusion algebra, then you can start thinking about what symmetries the various fields must have. So obviously in the Ising model there's a Z2 symmetry. So you can try to see if you can find some representations of the Virasoro algebra where there is the right Z2 symmetry. So for example, look at what the results are for the Ising model. Oh, that's an error. That should be m equals 3, I think. So my table gives me c equals 1/2. And there are 3 primary fields. One is the identity, which has h equal to 0, so that's not so interesting. Another one I choose to call the spin. It has h equal 1/16. And the third one is called the energy, denoted like that, and it has conformal weight 1/2. And the fusion algebra gives me that if I take two energy operators, they fuse just to the identity. Two spin operators fuse to the identity plus the energy, and spin times energy gives spin. So if you think about the spin as some continuum limit of just SI in the Ising model, and if you think of the energy as SI as J for nearest neighbors, some continuum limit, well then there's clearly some symmetry which is satisfied here. So for example, if you take two spins and approach them, it should give you either the identity or the energy operator. It can never give you another spin because that would violate set 2 symmetry. So it's possible to use symmetry also to identify models. So let me move to the last general topic, and then let me go on to something else. So I had these two different these two different algebras, Ln and Ln bar, and up till now they seem not to talk to one another. But actually they do if I put my theory not on the plane but on the torus. So I want to take two complex numbers, omega 1 and omega 2, and these two will span some lattice, and I want to identify points on that lattice. So the idea is that I take some omega 1 and some omega 2, and I see what lattice they span. And so, for example, this point here will be identified with this point here. So that's like having some torus, okay? So, of course, the partition function will depend on how tilted this torus is. So it will depend on the ratio between these two numbers. But it shouldn't depend on the individual choices of omega 1 and omega 2 if I span the same lattice. So obviously I could span this same lattice by taking some, instead of omega 2 like that, I could take omega 2 like that. So that's a very important remark. So let me write what the partition function is. So yesterday we saw how you could use some operator formalism to get the partition function by time evolving your system. So and yesterday we used this radial quantization. So we were sort of constructing the system by starting at the origin and going outwards. So here on a torus, it would be maybe natural to use this as my time direction and this as my space direction. However, this is not what I want to do. I want to use standard Cartesian directions. So this and this. So this is space, and this is time. And so the evolution operator is going to be a combination of this dilatation operator and then something else which is called the momentum operator. So the H will translate me in this direction, and the P will translate me in that direction. So once I write that down, I find that the partition function takes this form here. And now using the definition of my characters, it becomes this. So I see that the partition function shows me exactly how holomorphic and anti-holomorphic characters couple. And let me just keep it there. So clearly there is a lot of work that one could do here to try to find out what these coupling coefficients are. And let me just present you with one example of modular invariance, which will turn out to be very important for, there's going to be an end result which is very important for what I'll say next. So let me now do something that I haven't done until now. Let me just specify an action or an energy functional for some field. And so I'm just taking the most stupid thing that I can think of. I take what physicists call a free boson, so it's just a Gaussian integral over this field phi. But let me impose on it strange boundary conditions with respect to this torus. So the k and k prime are integers. So if I run down a couple of times along the periodic directions, then I will postulate that my field will pick up some contribution. So R is just an unspecified number, and these m here are live in some lattice. So what it means is that I'm identifying values of the field which differ by some integer times some number. So that is known as the compactified boson. So it means that instead of taking just real values, actually the phi lives on, so phi takes values so that certain points have just been identified. Okay, now I don't need really to do anything else than just compute directly the partition function. So those are Gaussian integrals. There's a small technicality that I won't speak of. But the thing is that you get out a result which is manifestly not modular invariant when I do it just for one specific choice of m and n prime. However, if I sum over all values of m and n prime, I discover something which is modular invariant. So let me take that as the definition of my partition function. It looks like this. It looks a little bit unwieldy maybe, but look what happens if I make use of the Poisson resummation formula in the variable m prime. Then it becomes this, which is exactly of the form that I wanted. Right? Let me go 2 slides back. It is exactly of this form here. And so since I know that L0 has as an eigenvalue the h's, I can read off directly the critical exponents, and the result is this. So just the requirement of modular invariance has completely specified the operator content of this theory. And so now in physics there is some terminology that people like to use. So people like to think of this E as an electric charge and M as a magnetic charge, but you shouldn't care too much about that. It's just some analogy with some electrostatic problem that people like to think about. So, but still they are called E and N, so anyway. But the bottom line is that I have specified all the operators. So, that was the end of yesterday's talk. And now we are moving to today's talk, but fortunately it's shorter. And now I'm hoping to get considerably more concrete. So now you can wake up again. So the second part here is dealing with the Coulomb gas construction and loop models. So we are moving closer to combinatorics, which was my goal after all. So I'm going to tell you first about loop models and the Coulomb gas. I'm going to present 2 examples of loop models that we can deal with pretty quickly because we already know them. I'm going to transform the loop models into height models, and I'm going to show how to write a field theory for those height models, which has the form of a conformal field theory. And I'm going to use that just building on the results that we have already seen to get all the critical exponents. So, the general strategy is the following. So the Coulomb gas construction applies to lattice model that somehow in the continuum limit become a collection of free bosonic fields like the one that we just saw. And as I'll show you, that will involve some complex Boltzmann weight, which will make mathematicians jump out of their seat, but somehow it's possible to deal with that and get exact critical exponents and much more. And it's especially well suited to combinatorial models of closed loops living on some lattice. And the main ingredients is, first, I try to make the loop model local. I transform it to a height model, and then I identify the corresponding compactified boson conformal field theory. That is to say, a field theory of the type that we just saw. Okay. Now, fortunately, I can go quickly because you know the Potts model from various talks. Spin variables take q different values. They live on some lattice. There's some aligning interaction between nearest neighbors. And as Alan showed us, there's this Fortuyn-Castelline representation in which the partition function is the sum over subsets of edges e to the j minus 1 raised to the power number of edges and q raised to the number of connected components. Of course, Alan will kill me because I didn't write the multivariate version of this, but I only need this. So that was this. What does that have to do with loops? Well, that's my next slide. Suppose now, for simplicity, that I just work on a square grid. And let's suppose that I have rotated my square grid 45 degrees, so that typically two vertices will look like this. Okay, if I'm on, okay, so now I go to what is called the medial lattice. So the medial lattice is another square lattice whose vertices are the midpoint of the edges of the original lattice. Okay, so the big circles here are on the original lattice. If there is a Fortuyn-Castelline cluster connecting these two guys, I will define a transition system, so these dotted lines here on the medial lattice, which will reflect off that guy. And if there is no such, if the Fortuyn-Castelline cluster doesn't live here, then I'm doing the opposite. And on sides of the other parity, I'm doing just the other way around. And then I'm just using the Euler relation, since the lattice is planar. And then I find that the partition function is equal to some uninteresting global factor, same sum over subsets, a slightly modified weight per edge. And then, crucially here, I get a weight of square root of q per loop made by these dashed lines.
Sorry, when you say connected by the cluster, you mean the edge belongs to E prime? Not connected from?
Yes, exactly. Okay. So it turns out now that the square lattice admits a duality transformation which will keep the lattice constant. And so it's possible to get the critical point of the Potts model in that way, and it turns out that at the critical point this factor here is 1. That was very nice, because then I don't need to count those edges anymore.
What is T of E prime?
What is T of E prime? T.
Number of loops.
The transition
T of E
system.
prime is the transition system you get from E prime.
Right.
And L of T of E prime is the number of circuits.
Loops, circuits, sorry. I was supposed to avoid that, falling into that trap. Circuits, not loops, but they are called loops in physics. I'm really sorry about that. Okay, let me define small n as the square root of q and go to this self-dual line, which turns out to be actually a critical point or a conformally invariant theory for n in this region here. Then I get just z equal the same uninteresting constant sum over these edges, and then this n, this weight n, raised to the number of loop circuit loops.
But this is what physicists would call a fully packed loop model.
Yes.
That is, on the medial graph, every
Right.
edge is occupied.
So you
and
just
the
have a
question is
you
how
just have
do
a
you
square
connect
lattice,
them?
and you just have a square lattice where at every vertex you can do this or that.
Is this equivalent to this model where you put mirror in every
Yeah, well, I guess that's the same thing. I mean, you can think of having a mirror like this or a mirror like that. So this is just exactly the same representation of the Potts model, but the one that I want to think about. Okay, next model, because I need two examples. I like to have two examples. Let's take the ON model. The simplest version of it lives on the hexagonal lattice. Maybe you can somehow skip all of this introduction here, which is kind of motivating how that model came into physics, and just take this definition here of the model. So the partition function is the sum over everything that you can write on the hexagonal lattice using these 4 different vertices. That is to say, either you leave a vertex empty, or you have a loop going by in any one of 3 possible ways. Okay? You put a weight k for each occupied edge, so the thick black ones here, and you put a weight small n for each circuit or loop that you form on the lattice. And so the big difference now is that you have empty space. So Nienhaus showed more than 25 years ago that if I take this particular relation between k and n, then the model is actually critical. And let's try to find out what the critical exponents are.
Can you just remind us what critical is?
Oh, sorry. It has a continuous phase transition. Correlations decay has power laws, and in this setup you can think of it as being conformally invariant. Okay, so now I'm going to show you how to take models of loops like that and transform them into height models. So you see here clearly something kind of bad is going on, because I have told you all the time that conformal field theories were kind of continuum limits of lattice models which had local interactions. And now I'm telling you that interesting lattice models have these loops where an enormous loop has a definite weight of n. How can that ever be a local thing? Well, that is what I'm going to recover now. So now I'm going to take my model of loops, think of the hexagonal lattice here, and I'm going to take each loop individually and I'm going to orient it, either trigonometrically or anti-trigonometrically. And now I'm going, for each time it turns an angle alpha, I'm going to attribute a weight to that turn which is exponential I alpha gamma over 2 pi. Well, okay, a small drawing would maybe be in order. So suppose I have some big loop, and now I draw this same loop twice with one orientation or the other, and I want the weight here, n, to be recovered as the total weight here and the total weight here. So this guy here turns a total of 2 pi, so it's going to get a weight e I pi, and this guy here,
Gamma.
Was it gamma? Yes.
Well, you also call it lambda.
Yeah. Gamma.
Every Greek letter other than alpha.
Excellent. Okay, so I get these weights, right? So if I now just postulate that n is parameterized as 2 cosine gamma, then this is an alright identity. And what I eventually is going to need is that n is comprised between -2 and 2, so that is a very nice parameterization for doing just that.
Sorry, I forgot the notation. N was the number of, it was the n1.
N was the weight for one loop. So the weight,
the n of the lemma.
right, yes. Okay, so the weight for the loop is the weight for this orientation of the loop plus the weight of the other orientation, and I can just sum out over those.
Two colors.
And so, for example, on the hexagonal lattice, that will give me, apart from the empty vertex, that will give me these 6 configurations here. And then my Macintosh went asleep, but it's being woken up. And so I get this thing here.
Lambda is gamma, which is something, parameter? Or
Gamma is nothing else than another way of writing n. I just fix n equal 2 cosine gamma, so you can forget about n and just say that it's specified by the value of gamma. It's just another parameterization.
Lambda is gamma.
Oh my god. Yeah, sorry. Yeah, and lambda is gamma. Gee. Yeah. I can do the same thing for the other model. So the model with these 2 vertices here on the square lattice. Actually, I can transform it into the so-called 6-vertex model. And that way. So imagine that all these loops here are being oriented also. Okay? And then let me try to, at a given vertex, just to retain the arrows, which are giving the orientations of the loops. So clearly there's going to be 2 incoming and 2 outgoing arrows. So that looks like what some people call the 6-vertex model. Okay, so there are 6 choices for doing that. So for example, if you take this first choice here, well, what could it look like in terms of oriented loops? Well, it can only be one thing. It can only be this. The transition system can only have been this, because if it were the other way around, then the arrow direction would change. Okay, right. This here is not allowed. And so that holds true for the first 4 of those. And for the 5th and the 6th, it's kind of funny, because this guy here I can resolve in both ways. So, now to get these correct weights for the turns, I should just say that the first 4 of them are easy to find. And I should remember also that there are differences between the even and the odd sublattice. And I have also set x equal to this weight per bond in the original edge, the edge weight in the original model. And so you see the 5th and the 6th are the interesting ones, because that is where these guys here turn, and the turns don't cancel out, and there are 2 turns.
I don't understand this notation, so you compare the components here. What does it express?
Oh, the notation means that I'm writing 6 equations on one line.
I understand.
Omega 1 equals 1, omega 2 equals 1, omega 3 equals x, and so on.
And the 2 lines are because
Yeah,
there are 2 sublattices that get treated
Because
differently.
there are 2 sublattices which get treated differently, because this thing here will, so this vertex here of the medial lattice will either stand on an edge of the original lattice, which is like this, or it will stand on an edge of the original lattice, which is like this. And the last line, I guess you can skip, because that's more for specialists on the 6-vertex model. And anyway, okay, and I should say that eventually x equals 1 was the interesting point, because that is when the model is self-dual.
Sorry, Jesper, I'm worried about a loop. So a loop is a closed walk which does not repeat edges. Is that right?
Yes, you just follow this as some path, and so eventually you'll get back to where you started.
Would it may go through the...
So it's a cycle. Okay.
Well, it's allowed to go through the same vertex twice.
No, it can't.
In this model, every edge gets used exactly once, because all the edges are occupied. It's just that at each vertex you put a non-crossing transition.
So it's a graph where every vertex has degree 2.
I think a loop could bounce off of both sides of the same edge in the original lattice.
Yeah.
Point here.
I believe you would call this a Eulerian circuit or something like
But I
that.
think Dave is right. The loop could bounce off both sides at the same vertex.
Oh yes, it could.
It repeats a vertex.
Oh yes, it should be possible to have a loop which will do something out here, come in like this, and do this. That would exactly correspond to an isthmus or a bridge of a 14-Castelline cluster.
But it's a circuit after you split along the transitions.
Yes. Yeah, that's exactly what it is. Okay, so I have shown now how to make these models local. And now I'm going to show you how I can transform them into a model of a compactified boson. So, and the boson is going to be nothing else than some height that I'm going to define right now. So if you were worried that you thought that a quantum field is something very abstract that you will never see, now you will see what it is geometrically. So in both my examples, I have now a vertex model with arrows sitting on the edges. And that's going to define me a height model in the dual lattice, because I can just say that, look down here, for example, whenever I go from one vertex on the dual lattice to an adjacent vertex on the dual lattice, my height will increase by A if I'm crossing an arrow which points to the left. And it decreases by A if my arrow points to the right. And if there is no arrow, it stays constant. So that's the rule. So, you know, it's like taking your favorite topographical map of somewhere where you want to go hiking. And curiously, I mean, these guys who make maps never put arrows on the contour line, so you can never see whether you're going up a mountain or if you're going down into a hole, except if you find the small figures that they write, and which are impossible to find most of the time.
Some maps you put this small.
I see. Okay.
Put small edge in the direction down here.
Okay. So I'm talking about that kind of a map. So these discrete heights are now supposed, in the continuum limit, to converge to some field which depends sort of continuously on the position. And what is the simplest possible energy functional or action that I can write down for such a field? Well, it is something like this. Some elasticity theory which will try to keep fluctuation down to a reasonable amount by assigning to them some positive energy.
Why do you have to compactify the boson?
Oh, that is an important point, which that's my next line, the gray line here, which...
Sorry, before you go on, Jesper, is the A that you use in defining the heights the same A that comes in the lattice spacing?
Yes.
Yeah, so you take them to 0 at the same rate?
Oh no, sorry. No. A is the fundamental height step.
Right.
It's not my mesh size of the original lattice.
So you don't take the height step and the lattice spacing to 0 at the same time?
Oh yes. I mean, to get something continuous in the limit, I have to take both of them to 0.
But not necessarily the same rate. There's some exponent that.
Right, and that's actually going to be linked to this G here.
Okay, so G is...
And so the G for now is not specified. And it's one of the major tasks that I have left for myself now, is to find out exactly what this G is. Because it's the G which will tell me how much wiggling around my height interface is going to make.
But I thought the compactification would involve another length than A. A would be like the
It will.
But you have these restrictions. It cannot jump too high from one level to another. I mean,
No, there's a fixed fundamental jump size. Of course, everything is going to be independent of that in the end.
somehow this is the main restriction of fluctuations, not
Yes.
some Hamiltonian. But somehow
I mean, the thing is that if I multiply A by 2, it means that the interface will fluctuate double wildly, so the G here is divided by 2, I guess. Okay, so now let's look carefully at this figure here. So I have to explain this kind of very carefully. So the thing is, I'm trying to convince you that this field here is compactified. If I shift it by 2A, it's the same thing. Why? Imagine your big hexagonal lattice. I've drawn here 3 faces, so corresponding to 3 sublattices. And imagine that I just repeat this figure throughout all of the plane. So on sublattice 1, I have a small oriented loop going anti-clockwise around. And it repeats itself, so there is a big number of such loops. And I write here the corresponding heights. So now I start gradually by making some of these, taking out some of these loops and changing their direction. So I do this so one loop at a time. So if I do it just once, I mean, I can imagine that all the other heights are being held fixed, but only the one in the center here is going to change to h plus 2a. Okay. Now I start doing, so and I gradually do that for all the circuits. So now I start doing something else. I take out this guy here and I put it over here, and I do it just a little at a time. And then there's going to be another change, and I go on doing small changes like that, and eventually I'll get back to the very same configuration that I started from. And if I can wake up this thing here, you'll see that when I go through a sequence of moves like that, all the heights in the end, I get back to the same configuration, but all the heights have been changed by plus 2a. But it's the same configuration, so I have to identify those. So by this kind of small trick, I see that phi must be living on the real axis, modulo 2a times an integer.
So is the point here that the loop model you're interested in is a model of unoriented loops?
Yes.
But you used oriented loops to define the height.
Yes.
So therefore, if you ask how does this bijection work, if you compare different orientations of the same loop configuration, it will correspond precisely to changing heights modulo 2. Is that right? That is to say,
right.
any 2 legal height configurations
Yes.
that are equal modulo 2 correspond to exactly the same loop configuration,
Yes.
possibly with some loops reversed, and conversely.
Even not
but
with
it was
some,
exactly
they're
the
not
same
even
orientation.
reversed, they have the same orientation.
Say this again?
They even have the same orientation.
you have
No.
exactly the same map, but you cannot tell what is the absolute height of the
Right. No, but I mean, what if you change
Yeah, but you
sites but not others?
I mean,
Modulo
there
2.
are 2 things that one has to distinguish very carefully. Of course, you will have noticed that I'm only defining height steps. So the absolute value of the height, you should say, is just not fixed. I'm not talking about that. That's something trivial. I'm talking about something a little bit more subtle, and that is that you can take some configuration where you have fixed the height at one place, say you fix it to 0 at the origin or something like that. Then you can go through a large series of small transformations where you just reverse a little loop somewhere or take out a loop or something. And every time you make a small transformation, you imagine that the large majority of the heights are kept fixed, and just the the height inside the loop that you're changing the direction of is being changed. And then in the end, you'll see that it's possible to generate a series of such transformations so that you get back to exactly the same microscopic configuration of oriented loops, but all the heights have changed by the same amount.
I didn't understand that. I didn't understand the step between the second and the third, and between the fourth and the fifth, where you actually changed what the occupied loops are.
Yeah.
I thought that the right statement would be, consider two loop configurations which are the same loops but differ by orientations. Then the height configurations are identical modulo 2. By which I mean that some sites but not others will go up or down by 2 or 4.
I believe
And
you can.
conversely.
You can maybe do it in your way as well. I mean, it's just a trick for finding this.
But what you just said about this, local perturbation, somehow this is based on the fact that your loops are only short. If you have a configuration with concentric loops like that,
yeah, but it works
then
for.
you will never somehow shift it by 2.
I can do it as well. It's just going to be more complicated. So this is just the simplest possible trick to get this periodicity of 2A.
He's claiming that there is a general fact. He defines heights on oriented loops.
Yeah,
And
then
then he asks, if you consider all the different orientations of a particular unoriented loop configuration, what do these height configurations look like? And I believe the claim is that they are always the same mod 2.
Yes.
And conversely.
Okay, so let's go on a little bit. So now I'm trying to find out what the conformal field theory is. So I already broke down this elastic piece of the energy or of the action. Now I have to say something about where do I define my theory. It turns out to be the easiest to define the theory on a cylinder, and then in the end I can transform it conformally back into the plane. So the theory lives on some cylinder. And I have shown you how to distribute locally this loop weight, but I haven't shown you what it means in the field theory yet. But let me talk to you about some other effect before doing that. Because imagine now that you're on a cylinder and that you have a loop which is winding around the cylinder. Well, something terrible happens then to what I just said, because this argument here clearly breaks down. This loop here will take as many right as left turns. So if I go through this same construction, it's going to get a weight of 1 plus 1 equals 2, completely independently of gamma. And so the cure for that is to say, let me draw a line like this, and let me give a weight e to the I gamma. No, not gamma. Yes, gamma. When I cross this line from left to right, and the opposite phase when I cross it in the other direction. Well, then clearly for small loops of trivial homotopy, I'm going to get exactly as many factors of those as of those, so they will cancel out, leaving the previous argument unchanged, whereas for loops being non-homotopic to a point, they will now pick up their correct weight. So that is fine. So let me now write down a second piece of the energy or the action which is supposed to correct for this fact. So it looks like this. Well, I just have to explain what R curly r is. So curly r is the scalar curvature. So now you're going also to jump up from your seats, I guess, because you'd say on a cylinder there's no scalar curvature. I consider scalar curvature in the sense that implicitly I'm always using the Gauss-Bonnet theorem. So if there is no scalar curvature here, there's at least some, what do we call it? Some curvature when going around the ends.
You imagine if there's some cap at the top and bottom of the cylinder?
Yeah, something like that. So so the Gauss-Bonnet theorem tells me that if I want to consider the scalar curvature in this sense, there's going to be plus 4 pi here and minus 4 pi down here. And so the end result is that this thing here with that definition is just going to count exactly the number of right arrows minus the number of left arrows that traverse this red line here. And so it's going to give exactly what I wanted. So what do we have up till now? So my partition function is this functional integral. And S consists of 3 pieces, of which I have talked about 2 of them. The first one was this elastic term. The second one was this boundary term here, which give a correct weight to loops that have non-trivial homotopy. And the last one, well, you can almost guess what it's going to be, because I haven't said a word about what the weight n of a loop which is homotopic to a point is and how it's to be put into the field theory yet. So something has to be done. And that's going to be the next topic. But I can already see now that this has the form of a compactified boson conformal field theory, where this E that I had just before can be identified with an E sitting up here in the exponential of phi. And the way that I see this is that, remember, my functional integral is always exponential of something. Okay, so that's where this exponential comes from. Don't be, I've been very careful about upright E's, which are exponentials, and these italic E's, which are these electric charges. So put on your looking glasses. And so you see that this term here, for example, is going to give me some factors of that type. And the other guys, the M's, that physicists like to call magnetic charges, well, those are height dislocations. In the sense that when I was on this torus here and I went around the periodic direction, I came back to a different value of the height. So there's another way that you can imagine doing that. Suppose that up till now we have only had closed cycles of loops, but suppose I insert some topological defect at some point. I say that there's an oriented loop segment going out, but it's never going to return here, it's going to be absorbed on some other point. Well, then if I use my height mapping, if I encircle this point here and if I count the number of height changes, it's going to be something non-zero. So it's a topological defect, and that's exactly what this M means. And now, since A is supposed to be unimportant, A was my fundamental height step, I might as well take a convention for it. Let me put it equal to pi.
Does this now mean that the fundamental field is no longer a scalar field phi, but it's a vector field which plays the role of gradient phi, except that because of these dislocations, this vector field is not actually a gradient. Its curl is not 0.
No, I mean the fundamental field phi is still just a scalar. It's just that now I'm allowing. So So I'm anticipating a little bit on how I'm going to compute critical exponents, but I will allow to insert a limited number, typical 2, of defects in my loop model, so that that there is outgoing arrows without ingoing arrows, and
But
the other
doesn't
way
that mean
around.
if phi is ill-defined?
Yes, now it's ill-defined, but I know exactly how it's ill-defined, and so it's ill-defined, and so it's a height dislocation. So it just tells me that when I encircle this point here, I'm going to make a screw dislocation in my height field. So I'm out of time. Let me just check. It would be nice to do this, just this last one here. So what about critical exponents now? Well, one thing that I maybe forgot to tell you is that the central charge of a free boson is 1. It's pretty easy to see because you know exactly what the functional integral is. So you know what the partition function is. It's a Gaussian integral. You can compute it. The stress tensor we saw last time is the functional derivative of z with respect to the metric. So that I can also compute. So I can construct the stress tensor. And I can take 2 stress tensors at different points and see what happens when I put them close together. That will give me this c/2 divided by distance to the 4th singularity that I can just plainly identify and get out what c is. And so it turns out that c is equal to 1, independently of the g. But now it's going to be something else because I have to correct for this extra term, this SB that I added to take care of these guys here.
What is G here?
G is the coupling constant of the here.
Okay, thank you.
So this SB here is going to change the central charge, and the way that you see it, kind of pretty easy because what this means is that I'm going to give there's going to be some height difference between here and here, which has exactly to do with the number of left crossings minus the number of right crossings of this line here. Okay? So when I go through my system, I can imagine that my height sort of steps up very gradually. Okay? If it steps up by a small amount, then I can imagine redefining my field. So let's suppose that this direction here of the cylinder is called T. Okay. Then let me write phi of, and this is x, phi of xt equals phi twiddle xt plus some t times a constant, so that the height difference between the two ends is going to be exactly the total length here, t times this constant, and so that this guy here has 0 height difference between the two ends. Of course, this guy here is going to be small, and I can just compute what its contribution to this term here is. And if I do that, I'll see that there's going to be a shift in the free energy, and the corresponding shift in the free energy is going to give me exactly this correction term here. So it's E0 squared because I had graph phi squared on the other transparency. And now finally, since we knew that it was a compactified boson, we had a formula, just my last slide of the first talk that I ended today, which was exactly like this, except that there was no E0, but so the E0 can be put into that formula as well. So let me finish now. So the remaining problems are that we haven't said anything about the bulk loop weights. So bulk means weights of loops which are homotopic to a point. I haven't defined SL. The two are of course going to be related. And most crucially, I have this coupling G here. I would like this coupling G to be a well-defined function of this n. That is really the crucial ingredient which is missing. Because what you can see is that if n is enormous, if n goes to infinity, it is clear that G also goes to infinity. Because if n is very large, it means that all your loops are small. If all your loops are small, it means that your height interface is completely flat. So it can only be flat if there's an infinite penalty for it to make elastic fluctuations.
But I thought n was only going to be between -2 and 2.
It is,
You don't get
eventually.
conformal field theory otherwise.
That is true, but somehow I'm going to sell you an argument that whatever G is, it should be a monotonically increasing function of n. So if I can relate those two, I will have solved the theory. And then I can extract critical exponents. So I'm going to harvest all of that tomorrow. And then in the third part of my talk, which is going to sort of be rushed through tomorrow at whatever price it takes, I'm going to apply this to a problem of real combinatorial interest. I'm going to solve for you the problem of the asymptotic behavior of Hamiltonian walks and Hamiltonian cycles on the square lattice and on the hexagonal lattice. And I'm going to show something hair-raising, that the two different problems, so Hamiltonian walks on the square lattice and on the hexagonal lattice, do not have the same critical exponents, contrary to what physicists would have believed when they talk about universality. You know, I mean, Alan has been advocating this all the time. He has been saying, you know, take an Ising model, put nearest neighbor interactions or 17th nearest neighbor interaction. It doesn't matter. Here, it does matter.
Because it's not
So
surprisingly
you commented on taking n to infinity. So are you saying, I still don't understand that, are you, I mean, Nienhuis, of course, limited n between -2 and 2. So are you saying you can get the critical behavior of the spherical model by a Coulomb gas?
No, I was just giving a very heuristic argument that G should be an increasing function of n.
But you're not actually going to go above n equals 2.
No.
No, I was just saying, I guess I'm not surprised that Hamilton cycles are a different universality class on square and hexagonal lattices, because, I mean, you're occupying everything. It really is very lattice dependent.
Right.
It's not like an Ising model.
Yeah, that is true enough. But so eventually I'm going to be able to say something about what is the probability that the two ends of a Hamiltonian walk are separated by a certain distance r. So asymptotically, what does the probability go like in r? And so the corresponding power laws can be derived exactly using this setup. So that is going to be my application.
For the Ising model, actually, this universality is essentially Tom Spencer and this what is his name? This arrow, this.
Okay.
And we thank Jesper for a very interesting talk.